Chapter 14, question 14, asks you to write the balanced chemical equation for the ionization of a couple amines in water. Well, the first step is to draw the amine. Now, the backbone is always a nitrogen atom whose name is amine. Now, if you remember, nitrogen is in column 5A, or group 5A on the periodic table, and that means that it has 5 valence electrons, and so can form 3 bonds with those unpaired electrons. We have a branch coming off of the nitrogen, and the prefix is meth, so here that's just 1 carbon. We know it's a branch because it ends in YL. Off of those other 2 bonds to nitrogen are hydrogens. And so that is methylamine. Let me write that just all in one color. So we have that nitrogen, hydrogen, hydrogen, and then this methyl group there. Okay, so that's methylamine. Now, amines are basic, or alkaline. They're the opposite of acidic. They're basic because they're all derivatives of ammonia. You could imagine the simplest sort of amine would be nitrogen with 3 bonds all to hydrogens, and that's ammonia. When we learned about acids and bases, ammonia was the poster child for the Bronsted-Lowry acid, or base, for Bronsted-Lowry base. So remember, in the Bronsted-Lowry definition, an acid donates a proton, and a base accepts protons. Now, protons are really H+ ions. If you look at the periodic table, hydrogen has only 1 proton in its nucleus. The number above the H symbol in the box is 1. That means it only has 1 proton. So a hydrogen atom is a proton with an electron going around it. If it loses the electron to become H+, then it's just a proton. So H pluses are the same as protons. And so this Bronsted-Lowry definition is really referring to the fact that acids can donate H pluses. For example, HCl, hydrochloric acids, the acid in your stomach, can donate this H+, or phosphoric acid, an acid that they put into Coca-Cola, can donate those H pluses. And a base can accept H pluses, accept protons. Now, one base that we saw was hydroxide. That has a negative charge, and it's that negative charge and the lone pairs on the oxygen that can accept the H+. But another molecule that has lone pairs that could accept an H+ is ammonia. Because of that lone pair at the top, it can accept an H+ and become ammonium. So notice how these electrons attacked an H+, and then ammonia turned into ammonium. So you can see that ammonia is able to accept protons, and so it's a base. And amines have that same lone pair, and because of that, they also can act as Bronsted-Lowry bases. Now in this reaction, they want to see these amines react with water. So we're going to take our methylamine and we're going to add it to water. And I'm going to write water as HOH just so it's really clear what's happening here. I'll write that there. I'll write these 2 like that. So this methylamine is going to act as a base, and what that means is it's going to accept an H+. So it's going to accept an H, and it's going to accept a plus charge. The rest of the molecule is all going to stay the same. We still have the methyl group at the left. We have the 2 hydrogens. That lone pair, though, is going to become a bond, and it's going to become a bond to the hydrogen that it accepted. So we showed it accepting an H. It also accepts a plus charge. Okay, so that's the amine. Now the water lost an H and lost a plus. It started with 2 H's, now it just has 1. It started with 0 charge, it lost a plus, and now it has -1. And this is the balanced chemical equation that you get when this amine, methylamine, ionizes. You know these are ions because they have charges, ionizes when you add them to water. Let's try that process with one more molecule. You'll see that the reaction is actually completely the same. The only difference are the branches coming off of the nitrogen. So first, let's try to draw this dimethyl amine. If you see the suffix amine, instantly know to draw nitrogen all by itself. Then we have branches. We have 2 branches that are of the same type. That's why we have that prefix di. How many carbons are in these branches? The prefix is meth, and that means that we have only 1 carbon in this branch. So in each branch. Now we have 2, so that's 1 methyl group. That's another methyl group. There you have dimethyl. Nitrogen always has 3 bonds, and so the third one is going to go to a hydrogen. And last but not least, we've got that lone pair at the top that makes it basic. So I'm going to redraw this all in one color so that we can think about it a little more clearly. And actually, I'm going to put the lone pairs in gray like last time so we can follow how they change. So this is our dimethylamine. Now, we're going to be adding this to water, so plus H2O. I'm going to write it as HOH just so it's really clear what's happening. And you get a reaction. Now, because of the lone pair on the amine, that amine is slightly basic and can accept H pluses according to the Bronsted-Lowry definition. The rest of the molecule stays the same, so we still have the 2 methyl groups, we still have the hydrogen, but now that lone pair is in a bond to the H that it accepted, that the molecule accepted. It didn't just accept an H, it also accepted a plus charge, and that plus charge is going to be on the nitrogen. So that's that first ion, and the second one, the water lost an H and lost a plus charge. It's acting as an acid in this reaction. And so it started with 2 H's, now it only has 1. It started with a 0 charge. If it lost a plus charge, now it has a negative charge. And so this whole reaction is going to be the balanced chemical equation for the ionization. And again, you know it's ionization because there are charges. Those charges make those ions. So you create ions in this reaction, so it's an ionization for dimethylamine in water.